We begin our journey at the
In the
edge of the
unending
Milky Way,
blackness
a
between the
vast
stars,
spiral of
there are
stars.
wanderers, worlds without suns cast adrift from their stellar nurseries, or perhaps formed in solitude from the very beginning. They are the lost children of the galaxy roaming the interstellar void in a state of perpetual twilight. We call them rogue planets, but this name belies their true nature. They are not merely planets, nor are they quite stars. They occupy a mysterious transitional realm, a cosmic borderland where the rules of celestial bodies blur. These lonely objects are known as brown dwarfs, the failed sons of the cosmos. They possess insufficient mass to ignite the nuclear furnace in their cores that would grant them true stardom. Instead, they smolder with a faint residual heat glowing dimly in the infrared spectrum, invisible to the naked eye. For millennia they were ghosts, their existence only a whisper, in theory phantoms haunting the calculations of astrophysicists. But now we can see them, we can measure their faint light, and begin to unravel their secret. 20 light-years from Earth in the constellation Cetus drifts one such solitary world. It has a designation, a string of numbers in a cosmic catalogue, SIMP J013656, 5 plus 093347. But its identity is far more profound. It is a world larger than Jupiter, yet not a star. A world with a surface temperature hot enough to melt lead. A world that spins on its axis with bewildering speed, completing a full rotation in just under 2.5 hours. And on this furiously spinning, isolated globe there is weather. Storms of a kind so alien, so extreme, they defy our terrestrial intuition. It is a realm of eternal violent change. And for the first time, from across a gulf of 200 trillion kilometers, a team of scientists at McGill University has charted its skies. They have created the first weather map of a lonely world, revealing a dynamic climate of incandescent clouds and metallic rain. This is the story of how we learn to read the tempests on a distant world, a story that redefines our understanding of what a planet can be. The idea of such in-between worlds is not new. It began as so much of astronomy does with Jupiter. When Galileo first turned his rudimentary telescope toward the heavens, he resolved the king of planets into a disk, a world with its own orbiting retinue of moons. Centuries later, more powerful instruments revealed its true character, a turbulent, dynamic atmosphere of swirling bands and colossal vortices. The Great Red Spot, a storm larger than our entire planet, has raged for at least 300 years, a testament to the power of planetary weather. Jupiter, however, is a subject of a star. Its climate, while mostly internally driven, is still influenced by the distant sun. Theorists began to wonder, what if a world like Jupiter were much, much larger? What if it had no star at all? In the 1960 seconds, the Indian-American astrophysicist Shiv S. Kumar was contemplating the lower limits of stardom. He calculated that there must be a minimum mass for a contracting cloud of gas to achieve the core temperatures and pressures necessary for sustained hydrogen fusion, the engine of a star. Below this threshold, somewhere around 75 times the mass of Jupiter, the stellar furnace would fail to ignite. The object would contract heat up from the compression of gravity, and then over billions of years simply cool down and fade away. He called these objects black dwarfs, though the name would later change. Around the same time, a young graduate student named Jill Tarter, who would later become a giant in the search for extraterrestrial intelligence, independently came to a similar conclusion, coining the term brown dwarf. The name was chosen not because of their color, but to signify their intermediate nature, a blend of a red dwarf's faintness and a black dwarf's darkness. For decades, these cosmic embers remained purely theoretical. The challenge of finding one was immense. They would be extraordinarily faint, emitting almost no visible light. Their feeble heat could only be detected in the infrared portion of the spectrum, a wavelength of light to which our atmosphere is largely opaque. Discovering a brown dwarf would be like trying to spot a warm fireplace poker from 100 kilometers away in the middle of a blizzard. It would require a new generation of telescopes placed high on remote mountaintops, or even better, in the cold vacuum of space, far above the obscuring veil of Earth's air. The search was a painstaking process of elimination. Astronomers scanned the sky for objects that were exceptionally red and faint, hoping to catch the telltale signature of a cooling substellar body. Many candidates were found, but confirmation was elusive. Was it a true brown dwarf, or just a very small, very distant red dwarf star? The breakthrough finally came in 1995. An international team of astronomers surveying the Pleiades star cluster identified a tiny faint object they named Tida-1. Its spectrum revealed the presence of lithium, a fragile element that is quickly destroyed in the core of a true star. The presence of lithium was the smoking gun proof that Tide-1's core had never reached the temperatures required for full-fledged fusion. It was the first confirmed brown dwarf. Almost simultaneously, another team using the Hubble Space Telescope imaged a companion to the star Gliese 229, an object called Gliese 229b. Its spectrum showed vast quantities of methane, a molecule that can only exist in an atmosphere cooler than any known star. The hunt was over. The celestial ghosts were real. An entirely new category of object had been added to the cosmic zoo, a bridge connecting the familiar realm of planets to the fiery domain of stars. So, what precisely is a brown dwarf? To understand this strange celestial entity, consider an analogy. Imagine the universe as a grand cosmic workshop filled with an infinite supply of building materials, primarily hydrogen gas. If you gather a modest amount of this gas, say the mass of Jupiter, gravity will pull it together into a sphere. The pressure in its core will build, but it will never be enough to spark a fire. You have constructed a gas giant planet, a cold, dark orb. Now imagine you gather a truly enormous amount of hydrogen, 100 times the mass of Jupiter or more. The gravitational pressure at the center of this colossal sphere becomes unimaginable. The hydrogen atoms are crushed together with such violence that their nuclei fuse, releasing a tremendous burst of energy. You have built a star, a self-sustaining nuclear reactor that will blaze for billions of years. A brown dwarf is what you get when you gather an amount of material that falls between these two extremes. It is the in-between creation. It is massive enough, between roughly 13 and 80 times Jupiter's mass for gravity, to generate immense core pressure. This pressure is sufficient to ignite a limited temporary form of nuclear fusion. It cannot fuse ordinary hydrogen, but it can fuse a heavier isotope called deuterium. This deuterium burning is like the brief sputtering flare-up of damp kindling. It provides a modest source of energy for a few million years, a fleeting moment of near stardom. But the deuterium supply is quickly exhausted. The fire goes out. The object then begins its long, slow process of cooling, glowing only with the trapped heat of its formation, a cosmic ember fading over eons into utter blackness. They are not failed stars. They are simply a different kind of cosmic object, obeying a different set of rules, living out a different kind of existence. Our particular subject, SIMP, exists right at the most intriguing boundary. With a mass estimated to be just over a dozen times that of Jupiter, it straddles the hazy line that separates the most massive gas giants from the least massive brown dwarfs. This makes it a perfect laboratory for studying atmospheric dynamics in a world untethered to the overwhelming influence of a parent star. Unlike the hot Jupiters we find orbiting other suns which are tidally locked and blasted by stellar radiation, SIMP generates its own weather from the inside out. Its climate is a pure expression of its internal heat and its astonishingly rapid rotation. It is a pristine test case for the physics of giant atmospheres, and it is this pristine nature that drew the attention of researchers at McGill University. Professor Nicholas Cowan and his team were fascinated by a subtle yet persistent puzzle. Observations from space telescopes like Spitzer and Hubble had shown that SIMP's brightness was not constant. It varied rhythmically by a few percent over a regular period of 2.4 hours. Something on this world was changing as it spun, altering the amount of infrared light it radiated into space. The most likely culprit was clouds. But what kind of clouds could exist in an atmosphere where the temperatures exceed 1,000 degrees Celsius? And how could one possibly map them on an object so distant it appears as a single unresolved point of light? The task seemed impossible. It's a challenge akin to trying to describe the continents of Earth by observing the flicker of a single candle held in front of the globe from the moon. You cannot see the shapes directly. All you have is the single integrated point of light. The key the team at McGill realized lay in time. By watching that single point of light for long enough and with enough precision, one can decode the information hidden within its variations. They developed a technique that is a masterpiece of scientific ingenuity, a method for turning the flicker into a map. Imagine you are standing on a shoreline at night, looking out at a distant fog-shrouded island. On this island is a single powerful lighthouse, and it is rotating. You cannot make out the shape of the island or the lighthouse itself. All you can see is its beacon, a solitary point of illumination. As the lighthouse beam rotates, its brightness appears constant. But now imagine there are large, dense banks of fog drifting between you and the island. As the lighthouse beam spins, it sometimes passes behind a thick patch of fog. When this happens, the light you see dims slightly. When the beam emerges from behind the fog bank, it brightens again. If you were to meticulously record these fluctuations in brightness over many rotations, you could begin to deduce the structure of the unseen fog. A long, slow dip in brightness might suggest a wide, extended bank of fog. A sharp, quick flicker might indicate a smaller, denser patch. If the pattern of dimming and brightening repeats with every rotation, you know that the fog banks are stable, long-lived features. You have, in effect, created a one-dimensional map of the obstructions around the lighthouse. The McGill team applied this very principle to SIMP. The brown dwarf is the lighthouse, its internal heat providing the light. Its atmosphere is the foggy sea filled with clouds. As SIMP rotates every 2.4 hours, different regions of its atmosphere turn to face Earth. Some of these regions are relatively clear, allowing us to see deeper into the hotter layers of the atmosphere. These clearings act as bright spots. Other regions are covered by thick, opaque clouds. These clouds block the heat radiating from below, making those parts of the atmosphere appear cooler and dimmer in the infrared. They are the dark spots. By using the Spitzer Space Telescope to stare at SIMP continuously, the researchers created a highly detailed light curve, a graph plotting the object's infrared brightness over time. They saw a clear, repeating pattern. The light curve rose and fell in a complex but stable rhythm, a signature etched into the light by the planet-girdling weather systems below. This rhythm was the key to unlocking the map. It was the language of the clouds, and the scientists were finally learning to translate it. The translation process was a computational tour de force. By modeling how different arrangements of bright and dark spots would affect the overall light from a rotating sphere, they could work backward. They could test countless possible maps, generating a theoretical light curve for each one, and compare it to the real data collected by Spitzer. The map that produced a light curve most closely matching the observed one was the most likely representation of SIMP's actual cloud cover. The result was breathtaking. For the first time, humanity had a plausible, data-driven picture of the large-scale weather on a rogue world. It was a glimpse into a climate more alien than anything in our solar system. The map revealed a world of stark contrasts. It showed large-scale banded structures reminiscent of the belts and zones of Jupiter. But the composition of these bands was utterly unearthly. The clouds on SIMP are not made of water ice or ammonia crystals. The temperatures there are far too high for such familiar substances. Instead, the models suggest these clouds are composed of molten silicates and iron, droplets of liquid rock and metal condensed out of the cooling atmospheric gas. Imagine vast continent-sized storm systems, not of water vapor, but of glowing molten lava and incandescent iron swirling through an atmosphere of superheated hydrogen. The dark bands on the map are these thick canopies of rock clouds obscuring the hotter layers below. The bright zones are clearer regions, holes in the cloud deck, where we peer down into the fiery depths of the brown dwarf's churning interior. It is a weather system forged in a furnace. The temperature difference between the cloudy and clear regions is significant, hundreds of degrees. This thermal gradient is the engine of the weather. It drives ferocious winds that likely scream across the planet at thousands of kilometers per hour, far faster than the most violent hurricanes on Earth. The planet's hyper-fast rotation whips these winds and storm systems into the observed east-west bands, a phenomenon of the Coriolis effect amplified to an almost unimaginable degree. This is not weather as we know it. It is a form of geology taking place in the sky, a cycle of vaporized rock rising on massive convective currents, condensing into droplets of magma and iron at high altitudes, and then raining back down into the crushing incandescent depths. The sky over SIMP would not be blue or grey. It would be a swirling, self-luminous tapestry of dark silicate fog and glowing orange chasms all streaking by at supersonic speeds. What would it be like to witness this spectacle firsthand? Let us imagine a hypothetical probe built of impossible materials descending into SIMP's atmosphere. The first thing it would notice is the light. There is no sun here. The illumination comes from below. The planet itself glows with its own heat, a dull, cherry-red radiance emanating from the very air. Looking up the sky would be a maelstrom of activity. Vast dark shapes, the continents of iron cloud, would sweep overhead, plunging the probe into a deeper twilight. Then a break in the clouds would appear. Not a patch of blue, but a blindingly bright rift, a window into the furnace below, illuminating the surrounding cloudscape in a hellish orange glare. The brightness of the entire sky would fluctuate dramatically, not on a cycle of day and night, but on a chaotic 2-hour cycle driven by the passage of these colossal planetary-scale storm fronts. There would be sound, the constant shrieking howl of winds moving at speeds that mock comprehension, the deep resonant rumble of convection cells the size of terrestrial countries carrying heat from the planet's core, and perhaps the most alien sound of all, the percussive hiss of the rain. Not water, but droplets of iron and molten glass cooling and solidifying as they fall through the upper atmosphere, becoming a downpour of hot metallic sand. It is a world of perpetual, violent, and utterly magnificent storm. The map created by the McGill team is more than just a remarkable technical achievement. It is a profound step forward in a much larger quest, the characterization of worlds beyond our own. Brown dwarfs like SIMP are a crucial stepping stone. They represent a simplified model for understanding the even more complex atmospheres of the thousands of exoplanets we are now discovering with missions like Kepler and TESS. Many of these exoplanets are gas giants orbiting perilously close to their stars. Their atmospheres are shaped by a complex interplay of internal heat and intense external radiation. Disentangling these effects is incredibly difficult, but a lonely brown dwarf has no external radiation to complicate the picture. Its weather is a pure product of its internal physics. By successfully modeling the clouds on SIMP, we build and calibrate the tools we will need to understand the atmospheres of planets that might one day be considered potential abodes for life. SIMP is our atmospheric Rosetta Stone. The future of this research is incredibly bright, and its new vanguard is the James Webb Space Telescope. Where Spitzer could only measure the total infrared brightness, JWST can dissect that light with breathtaking precision. It can perform detailed spectroscopy, breaking the light from SIMP into its constituent colors or wavelengths. Within that spectrum are the chemical fingerprints of the molecules and elements that make up the atmosphere and the clouds. With JWST, we will move beyond simply mapping the location of clouds. We will be able to determine their composition with far greater certainty. We can measure the size of the silicate dust grains differentiate between clouds of iron and clouds of other exotic minerals like corundum or perovskite. We might even be able to map different cloud layers at different altitudes, creating a true three-dimensional weather map. We will be able to measure wind speeds directly by observing the Doppler shift in the spectral lines. We are standing on the threshold of a new era of comparative climatology, one where Earth's weather is just one data point among countless others. This journey from a theoretical twinkle in an astronomer's eye to a detailed weather chart of a world 20 light-years distant is a testament to one of humanity's most defining traits, an insatiable and audacious curiosity. We are pattern seekers, map makers. We are not content to simply look at the points of light in the sky. We are driven by a deep fundamental need to understand what they are, to transform them from abstract data into tangible places. To imagine their landscapes, to feel their winds, to chart their storms. SIMP J013656 5+093347 floats in an eternal solitary darkness. It is an orphan of the galaxy bound to no star, following its own lonely path through the cold, diffuse medium between suns. It is by any human measure the epitome of isolation, and yet it is not entirely alone. From across an ocean of space-time so vast it defies analogy, a species of curious primates on a small blue world has reached out. Not with hands, but with intellect and ingenuity. We have watched its faint, rhythmic breathing of light. We have listened to the story it tells. We have drawn the first lines on a new kind of map, charting the climate of a world we can never visit. The universe is not only stranger than we imagine, it is stranger than we can imagine. But with each new discovery, with each distant weather report, our imagination grows and the cosmos becomes just a little less lonely for us all. The Atlas of Worlds is open, and we have only just begun to fill its pages.